Good morning, all. I just posted the YouTube link in the chat. So please help to share for those that can't join the class. I just posted the YouTube link again. So you can help me share the YouTube link to those that won't be able to join the Zoom link. Please post the YouTube link. I just posted it. If you can see it, just give me a thumbs up. If you have seen the YouTube link. Okay, thank you. So please help to post. Thank you. So post the YouTube link. And please, all through this lecture, don't unmute yourself. If you unmute yourself, I will remove you from the class and put you in the waiting room. You will not be able to join the class again. All through this lecture, do not unmute yourself. If you do that, I will send you to the waiting room and you will be there at the end of the class, or you go and join the YouTube link. So please, make sure you are muted all through this lecture. Christiana Adebowale, can you bring down your screen or I will remove you from this lecture? Christiana Adebowale, this is the last warning. Bring down your screen or I'll remove you from this lecture. If anybody shares screen again here, I will remove that person from this lecture. This is your last warning. You are just to listen to lecture. You are not to do anything. If I ask you a question, you put it on the chat. If I see anybody's screen up, I'll remove you from the lecture. So we'll just wait for 9 o'clock so we can start our lecture. Just share the YouTube link, please. So I believe by now you can see my screen. Please, can we confirm if those that join via YouTube can see the screen and if they can hear me? Is there any way we can confirm? So you just put it in the chat. I mean, okay, you can see and you can hear, fine. What about those via YouTube? Okay, okay, thank you. So I just want to confirm that those on YouTube can hear and they can also see my screen, okay? Okay, thank you so much. So both on Zoom and YouTube, you can see and you can hear. So let's just wait for a few minutes. Once it's 9, I can start. So good morning, everyone, and welcome to FSC 112/CHM 101. So Dr. Schweib, I've already done his own part. So I'm the second lecturer. I'll be taking you today, Wednesday. We'll also meet on Friday. Then I should be able to round up on Monday before another lecturer comes on board. So each lecturer that comes will be taking you at least for 3 periods. So today I'm starting, and my name is Dr. Ejia, E-J-I-A-H. That is my name, Dr. Ejia. And for my own part, we are going to be looking at the trends of atomic radii, ionization energies, and electronegativity of the element based on their position in the periodic table. So invariably, we are going to be looking at the periodic table, the periodic properties, and the trends. That is going to be the first lecture for today. And after that, we are going to look at chemical equations chemical reactions, and stoichiometry. And we're also going to carry out some calculations based on these chemical reactions we are going to be looking at. And finally, we are going to look at the limiting reagent, the limiting reactant concept. So those are the topics I'm going to be taking you for the 3 lectures I will be having with you. So first, as I said, today we are starting with the trends of atomic radii, ionization energies, electronegativity of the element based on their position in the periodic table. So this is the modern periodic table. And if you look at this periodic table, just from the word table, so you see that this periodic table is just like a table. You equate it like a table. And if you look at it, you have all the elements. And these elements are arranged either, we can arrange either in periods, these are the periods, or the groups. When we talk about period and when we talk about group, what do we mean? For period, these are usually horizontal rows across the periodic table. So the horizontal rows across, so the periods are across the periodic table. So they are the horizontal rows across the periodic table. What about the group? When we talk about the group, these are vertical columns down the periodic table. So these are the vertical columns down the periodic table. So invariably, if you look at this periodic table based on the period and the groups, we see that the atomic number increases as you move down a group or across a period. So if you look at it across, this is hydrogen is 1, helium is 2, lithium is 3, beryllium is 4. So as you go across, the atomic number is increasing. Likewise, if you look down the group, you see that this is hydrogen is 1, lithium is 3, sodium is 11. So across and down the group, you see that the atomic number is always increasing. Now, having talked about that, what is a periodic table? We said the periodic table is a tabular arrangement. So you see that word table. It's a tabular arrangement of elements in the order of increasing atomic number. So this is actually what I've explained looking at the previous slide of your periodic table. So when we talk about the atomic number, we are actually talking about the number of protons. Now, having looked at the periodic table, the last slide, we talk about we have what we call periodicity. When we talk about periodicity, that is something that occurs at every interval. So periodicity is actually the occurrence of similar properties at regular intervals with increasing atomic number. So this is actually what is known as what? Periodicity. Now, before we go on to the periodic trends and the electronic configurations, let's look at a brief history of our periodic table. The periodic table, the work was actually done as far back as the 19th century. And the periodic table was developed by chemists such as Newland, Lothar, and most especially Mendeleev. So the periodic table we are actually using is the one developed by Mendeleev. So this is actually, it was the Mendeleev periodic table, aside the other chemists, that led to what is known today as the periodic table. And in the periodic table again, you also have what is known as the main group elements, and we have the transition elements. So you can classify it, aside classifying it based on group and period, you can also look at the periodic table in terms of the main group and the transition element. And the main group are usually referred to as the A subgroup, while the transition elements are referred to as the B subgroups. Aside that, you can also classify the periodic table based on the S block, the P block, where the S and the P block are usually numbered as groups from group 1 to 7. or what we call group 0, that is the group 8. You can also classify it as a D block or F block. So this is actually what we mean by S block, P block, D block, and the F block. So if you look at your group 1 and group 2, these are usually your S block elements. If you look at your group 3, 4, 5, 6, 7, these are actually your P block element. When we say they are S block or P block, what it means is that is when we get to the electronic configuration. What we mean by that is that the valence electron usually rests in these orbitals. So that is why we say they are S block or they are P block. And this is the D block. That is your transition element, and the lanthanide and the actinide are the F block elements. So you can actually classify your periodic table in different ways. You can based on period or group, based on S block, B block, D block, F block, or the main group and the transition elements. I hope you can hear me. If you can hear me, just give me a thumbs up. Okay, thank you. So now, let's look at the arrangement of the periodic table. We said that elements are arranged in order of their atomic number. I think I've already explained that. So you have your hydrogen, your helium, your lithium, your beryllium. So you see that the elements are arranged in order of their atomic number in the periodic table. So you go from 1, 2, 3, 4, 5, 6, and 8, etc. Also, the elements in each group have similar properties. Elements in each group. This is group 1, group 2, group 3, group 4, group 5. So we say that elements in the same group have similar properties, and we are going to see the reason why this occurs is because these elements have the same electron in their valence orbital or in their valence shell. And so elements show changing trends across the period, but on the same down the group, you see that the elements will show similar chemical and physical properties because they have the same valence electron. But across the period, you see that the atomic number is increasing, is changing. So elements show changing trends across the period. So let's now look properly at elements in the same group in the periodic table. We see that elements are arranged such that elements in a particular column, or what we call the vertical column, have the same number of electrons in its valence shell. If you look at lithium, this is group 1, lithium, sodium, potassium, rubidium. You see that your lithium is helium 2s1, your sodium is neon 3s1, your potassium is argon 4s1, your rubidium is tritium 5s1. You see that they all have, despite having different principal quantum number, that is 2, 3, 4, 5, that is the energy level is increasing. Despite having increasing energy level, which is the 2, 3, 4, 5, you see that the orbital, all of them have one electron in the s orbital. So the elements arranged in groups possess related chemical proper and physical properties because of this valence electron. So they will have similar chemical and physical properties because of the same number of valence electron that they have, despite the energy level. Now, let's now look at elements in the same period, but different groups in the periodic table. Each element in a horizontal row, or what we refer to as period, differs from the preceding element by addition of an electron to the electron shell and a proton to the nucleus. So you see, this is lithium, your beryllium, your boron, your carbon. So this is 3, 4, 5, 6. So there's actually a progressively increase in the atomic number. And because there's progressive increase in the atomic number. You see, your lithium is helium 2s, your beryllium is helium 2s2, your beryllium, you see now we have entered the p orbital, and we'll continue until we get to your 2p6, which is your neon, where you have the complete electronic configuration. Now, what this tells us is that because we are looking at elements in the same period, they are going to have different physical and chemical properties because they possess progressively increase, or they have a preceding element by addition of an electron. Unlike on the same group, they have the same valence electron, but here they don't have the same valence electron. As you go across the period, what happens is that the atomic number keeps increasing. So because of that, we say they possess progressively different physical and chemical properties. So this is actually the trend down the group and the trend across the periodic table. Now, having looked at the periodic table, let's look at the ground state electronic configurations of your elements for the outermost electron. Of course, this is your group 1, group 2. You see that if you look at group 1, you see that the valence electron is 1, despite the N. N, of course, is your the energy level. Your N is the period number to which the elements belong. N is the period number to which the elements belong, while the S1, S2 is the group number. So here the S1 is showing that this is actually our group 1 element. Your S2, this is showing that this is group 2. This is your group 3, 2 plus 1, 3. This is group 4. This is group 5. This is 6. This is 7. And this is 8. So the NS2P6 is actually telling us the group number, where the N is telling us the period number to which the elements belong. So let's take example. If we like your neon, let's say your neon, if you write the, this is the ground state electronic configuration, instead of you writing 1s2, 2s2, 2p6. So you can just write ns2, np6. This is actually telling us that the electronic configuration here, this group is actually group 8. And the electronic configuration, as I said, the normal for your secondary school, you write 1s2, 2s2, 2p6. So you can actually use this as the ground electronic configuration. So what that means is that if you know the ground electronic configuration for each of the elements, then you'll be able to write the electronic configuration. Knowing with this, you'll be able to know the group number. You'll be able to know the group number of each particular element. So it's very, very important that you know the ground state electronic configuration of the element using this method. You can also write your 1s2, 2s2, 2p6. But if you know this is a short form. With this, you'll be able to know that the ground state electronic configuration is going to be 1s2, 2s2, 2. So the last electron is going to be 6. And this is for neon. Now, having looked at the ground state electronic configuration and your periodic table, let's now look at the periodicity of elements. That is actually what we are more interested in, the trend of the periodic element. As I said, periodicity refers to the recurring trends that you normally observe in the properties of the elements in the periodic table, and they are usually caused by regular and predictable variations in element atomic structure. So just down the group and across the period, as the atomic number increases or changes, of course, we expect the periodicity of the elements to change. Now, looking at the periodic properties. The periodic properties will actually depend on their electronic configuration. So if you know, that is why we have looked at the ground state electronic configuration. If you know that the valence electron is 1, that means all the elements that we have 1 valence electron will have similar physical and chemical properties. And their periodic properties will also be similar. So the periodic properties will depend on the electronic configuration. So it's very, very important that you know how to write electronic configurations. And these properties, they repeat after certain intervals down the group of the periodic table. So what are some of the periodic properties that is known? We have the atomic radius, we have the ionic radius, we have the ionization energy, we have electron affinity, and we have electronegativity. So these are the periodic properties that have been studied. But for our lecture, we are only going to concentrate on three: the atomic radius, the ionization energy, and electronegativity. So these are the three that we are going to concentrate on. These are the three periodic properties. We are going to look at them. We are going to know what they are, and we are going to look at their trend down the group and across the period. Now, the first is your atomic radius. What do we mean by atomic radius? Atomic radius, how do we know the atomic radius of an element? We say this is half the distance between two nuclei of a homo diatomic molecule. I will take that again. If you look at this element, this is bromine. So what it means is that for you to be able to get the atomic radius, you have to have two nuclei of a homo, the same. This is bromine, bromine. Homo di, that means they have to be two of them, diatomic molecules. So half the distance. So if you look at this, this is half of this bromine, and this is half of this bromine. So the half distance between two nuclei of a homo diatomic molecule, that is the atomic radius, or that is the atomic radius. Now, having known the definition of your atomic radius, what is the trend? As I said, we are going to look at the trend across the period and down the group, and the reasons why we have these trends. So we said that atomic radius decreases across the period. Why? Due to the increase in the positive charge from the protons. So if you look at across the period, of course, we have our sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. So if you look at this trend, you see that we are going from the large size to a smaller size. One, because as you go across the period, what happens is that you are adding extra number of proton and extra number of electrons. So what it means is that the nuclear pool is actually increasing. So the elements are actually coming together. They're coming closer together because, as we said, increase in the positive charge from the protons. So you are going from 11, 12, 13, 14, 15, 16. So as the number of protons and electrons are increasing, of course, the nuclear pool is increasing. So we say that each added electron feels a greater and positive charge because the protons are pulling in the same direction. Mind you, you're adding that extra electron on the same shell. Unlike when you go down the group, you are adding the extra electrons on different shells. But across the period, you are adding the additional electron on the same shell. So what it means is that the nuclear pool is increasing. So atomic radius decreases across the period. So if it's increasing, of course, you know that the distance will also decrease. The distance between the two diatomic homonuclear, the distance between the homonuclear diatomic molecule will decrease. So we say that across the period, the atomic radius decreases. Of course, down the group, the atomic radius will increase. So now, what are the trends in atomic radius? What are the factors that can affect this atomic radius that is across the period is decreasing and down the group is increasing? One is the energy level. The energy level will play part when we look at atomic radius down the group. the energy level of the valence electron. Of course, down the group, we are going from 1, 2, 3, 4, 5, 6, 7. So the atom is getting larger, and the distance between the two homonuclear molecules will actually increase. So the higher the energy level, the further the distance from the nucleus. So distance from nucleus is in the order of energy, that is 1, 2, 3, 4, 5, 6, 7. So of course, as we go down the group, so the atomic radius will increase. So this is one factor that will affect your atomic radius. Another factor that will affect it is the nuclear charge. As I've already explained, that is the number of protons in the nucleus. So the higher the charge, the closer the electrons to the nucleus. Of course, the higher the charge, of course, as you go across the period, we are adding more electrons. So the higher the charge, the closer the electrons to the nucleus. That is, when you talk about the nuclear charge, you're talking about the atomic number. And we know that the atomic number increases as we go across the period. So the higher the atomic number, the smaller the size. Of course, the nuclear pool will be higher. Of course, I've already explained that, using from your sodium to your chlorine. Another factor that can affect your atomic radius is the shielding, or what we call the screening effect by inner electrons. What do we mean by the shielding or screening effect? This is the screening of outermost electrons from the nucleus by the inner electrons. You agree with me that across the period, there's no shielding effect. Unlike down the group, we have shielding effect. Of course, the first energy level will shield the second energy level. The second energy level will shield the third energy level up to the seventh energy level. So that is why the greater the shielding or screening effect, the larger the size. So as you go down the group, the atomic rate, the shielding effect increases, so the size increases. But across the group, there's no shielding or screening effect, so the atomic radius will actually decrease. So shielding or screening effect, this is the screening of outermost electrons from the nucleus by the inner electrons. So these are the factors that can affect your atomic radius. So that is for your atomic radius. Now we look at, so we have already known the trend in your atomic radius. So across the period, it will decrease, but down the group, it will increase. And we have already said the factors that will affect it: the energy level, the nuclear charge, and the shielding or screening effect. Now, we talk about ionization energy. So, why are you raising your hand? If you have is there any problem? Can you hear me? As long as you can hear me and you can see my slide, whatever question you have, put it on the slide. You can only raise your hand if you cannot hear me or you cannot see my slide. But any question you have, please put it on the chat. When we are done, we will look at the questions. You can only, oh, I should slow down. Okay. Okay, thank you. Thank you. I will slow down. But can you understand what I'm explaining? I will slow down. Okay, thank you. Okay, thank you. Thank you. So, but I want to believe that we understood the atomic radius across the period and down the group and the reasons. So the next is ionization energy. The next is ionization energy. When we talk about an ionization energy, we say ionization energy, that is your IE, is defined as the energy in kilojoule per mole required to remove the most loosely bound electron from an isolated gaseous atom to form a positive gaseous ion. I will explain this definition very well. Now, we said that is the energy required to remove. So what it means that you have to remove the most loosely bound electron. And this most loosely bound electron must be in the gaseous form to be able to form a positive gaseous ion. If you have, let's say you have your sodium metal, and you have it in your container, I will ask, can ionization energy occur in that sodium atom? If you just have it in that container, can ionization energy occur? No, because for ionization energy to occur, what it means is that it's required that you give some energy. Some energy has to be applied such that that atom will be in the gaseous form. It is only when it is in the gaseous form that it will be able to remove the most loosely bound electron to form a positive gaseous ion. So that is why it's very, very important for you to understand the definition of your ionization energy. So it's defined as the energy. So what it means that energy must be supplied to remove the most loosely bound electron from an isolated gaseous atom to form a positive gaseous ion. So now, if a small amount of energy is supplied to an atom, what will happen is that electrons can be promoted from a lower energy level to a higher energy level. But you need to apply the required energy for that electron to be removed. Sometimes you just apply the energy that is just enough to promote electrons from a lower end of energy supplied is not sufficient to not be removed. So invariably, you must supply the sufficiently large energy for that electron to be removed. So if a small amount of energy is supplied to an atom, electrons may be promoted to a higher energy level. But if the amount of energy supplied is sufficiently large, the electron may be completely removed. So that was what I was trying to explain. You must supply a sufficient amount of energy, not only to promote electron from a low energy level to a high energy level, but to be able to remove the electron completely for ionization energy to occur. So now, talking about ionization energy, we've already explained what ionization energy is. We have what we call first ionization energy, second ionization energy, third ionization energy, fourth, fifth. But they must occur sequentially. That means the first must occur before the second, before the third. You cannot just remove 3 electrons at once to get your plus 3 oxidation state. No, you must start with the first, the second, and the third. So what do you mean by the first ionization energy? The first ionization energy is the minimum energy, of course, in kilojoule per mole, required to remove an electron or to remove the first electron, because we are dealing with the first ionization energy. To remove the first electron from a gaseous atom, mind you, it has to be in a gaseous form, in its ground state, to form a gaseous ion. So if you look at this equation, this is your gaseous atom. That means energy is supplied to the atom to make the G here is shown that it's in the gaseous form to form the +1 oxidation state, of course, which is also in the gaseous form. Of course, there's a loss of 1 electron. So this is the first ionization energy. And for the second ionization energy to occur, it is the first ionization energy that will actually undergo a second ionization energy. And it is the second ionization energy that will undergo the third ionization energy. So that is how it works. So you can have up to 4, 5, 6, as much as you want, as much as electrons you want to remove. But there's also going to be a clause where you find it difficult to remove some electrons based on some factors. But just know that you can have your first ionization energy, second, third, fourth, fifth, so on and so forth, and know the definition of your first ionization energy is very, very important. And this is the trend. The first ionization energy, of course, the energy will be smaller compared to the second, compared to the third, because as you are removing more electrons, of course, you are entering more into the nucleus, and to remove these electrons will be more difficult. So ionization energy is always endothermic. What do you mean by endothermic? That means energy is added. So you must add enough energy to be able to remove the valence electron. So that is why we say ionization energy is always endothermic. So the energy required to remove an electron from an atom reduces as the size of the atom increases. So as the size of the atom increases, what happens is that the valence electron is further away from the nucleus, and the energy required to remove that valence electron will be small. So energy required to remove an electron from an atom reduces as the size of the atom increases. Mind you, as the size of the atom increases, the valence electron is further away from the nucleus. So if it's further away from the nucleus, of course, what it means is that you don't actually need much energy to remove that valence electron. But if the electron is close to the nucleus, you will agree with me that you need extra energy to be able to pull out that electron from the nucleus. So we said that ionization energy and atomic radius are inversely proportional in terms of size. So the larger the atom, the smaller the ionization energy, the larger the atomic radius. Of course, the atomic radius is the distance between both of them. So if the size is large, then the distance will be large. But if the size is large, then the energy you need to remove the valence electron will be smaller. So that is why we said that ionization energy and atomic radius are inversely proportional. That is in terms of size. The larger the atom, the smaller the ionization energy, the larger the atomic radius. So what are the factors that affect ionization energy? We have the nuclear charge, we have the shielding effect, we have the radius, and we have the sub-energy level. For the nuclear charge, of course, the larger the nuclear charge, the greater the ionization energy. If the nuclear charge is small, that means the nuclear pool is very strong. Of course, to remove the valence electron will be very, very difficult. So the larger the nuclear charge, the greater the ionization energy. What about the shielding effect? The greater the shielding effect, the less the ionization energy. When we talk about the shielding effect, we look at this in terms of when we look at the group. As we go down the group, there's more shielding because you have your 2s, your 3s, your 4s, your 5s, your 6s, your 7s. So the size is increasing, and your 2s is shielding the 3s. Your 3s is shielding your 4s. So as you go down the group, so that is what we mean by shielding effect. There's a shield from the valence electron. The inner electrons are shielding the outer electrons. So the inner electrons are closer to the nucleus. So the greater the shielding effect, the less the ionization energy. So what it means is that if you have electron in your 7s, of course your 2s, 3s, 4s, all those ones have shielded your 7s from the nucleus. So the shielding effect will be greater. So the greater the shielding effect, the less the ionization energy. Then the radius. The greater the distance between the nucleus and the outer electrons of an atom, the less the ionization energy. And the last but not the least, which I've not explained earlier, is the sub-level. When we talk about the sub-level, we are talking about the full or the half-full sub-levels. And these full or half-full sub-levels usually requires additional energy for the electrons to be removed. Why? Because for the full and the half-full orbitals, we are looking at your NS2 and your NP6. If you have electrons, if you have elements that have your NS2, that means the orbital is completely filled. There is stability. Likewise, your NP6, the orbitals are completely filled. When this happens, or your half-filled, that is your NP3, this is your half-filled orbital, this is your filled orbitals. Your NS2 and your NP6, they are the filled orbitals, and your half-filled orbitals is the NP3. So what it means is that this p orbital, you know that your p orbital is your px, you have your px, py, and your pz. Let me explain your half field first. If you have your biro and your notebook, I expect you to come to the class with your biro and your notebook so that you can be writing as I'm talking. So if you have your NP3, that means you have your PX, PY, PZ. We have your NP3. That means each of the orbital has one electrons in that orbital. What we are saying that is what we mean by half field orbital, and yes, maximum stability. It's as stable as when you have your PX, PY, and your PZ having two maximum electrons. So that is what we mean by your half field and your completely filled orbital. So when you have this type of orbitals in any of the electronic configurations, then you are going to have stability. You are going to have stability. I will take that again. Your full, this is the last, your sub level. An electron from a full or half full sub level requires additional energy to be removed. And that is why I have used your PX, your PY, and your PZ to actually explain what we mean by half filled and your completely filled orbitals. So for your NS2, of course, this has completely filled orbital and this has completely filled orbital. So you will agree with me that is going to be stable. Also, the half-filled orbitals. So these orbitals, for electronic configurations that will have these orbitals, that will have this electronic configuration, they are going to have a very high ionization energy. So they have higher ionization energy than is expected due to what? Reluctance of the orbitals to lose its stability. So that is factors that affect ionization energy. The nuclear charge, we've already explained, the shielding effect, the radius, and the sub-energy level. So now, let's look at the group trends in ionization energy. So when we talk about the group trends, we look at the first, second, third, fourth, and fifth ionization energy. So down the group, the first ionization energy decreases. Why would the first ionization energy decrease down the group? Because if you agree with me, down the group, as we go down the group, the valence shell is actually increasing. The valence electron is further away from the nucleus. So atomic radius of the atom increases, shielding effect increases. So invariably, the valence electron is very far from the nucleus. So the first ionization energy will decrease. But you see that as you go to the second, the third, and the fourth, depending on the electronic configuration, you now see that the ionization energy might start to increase because now you are going further into the nucleus. Now, this is a table of your first ionization energy. If you look at your helium, this is your hydrogen, lithium, sodium, potassium, and rubidium. If you look, you see that you are going from your 1s, 2s, 3s, 4s, 5s. So you agree with me that the valence shell is increasing. The size is actually increasing. And you see that the first ionization energy is reducing because the valence electron is very far from the nucleus. So you don't actually need much energy to remove the valence electron. So the first ionization energy down the group is usually small. If you look at the first ionization energy, you see that as you go down the group, it's actually reducing. And we have already given the reason. Now, what about across the period? What about across the period? Atoms in the same period have valence electrons in the same energy. So across the period, we have the same energy. We have the shield, there's no shielding effect. The electrons are being added on the same orbital, on the same shell. So there's no shielding. There's no shielding of valence electron. So they have the same shielding. So the nuclear charge increases across the period, because across the period, you are adding the same electron on the same shell. So what happens? You are increasing the number of protons and the number of electrons. So the nuclear pool is increasing. So ionization energy generally increases from left to right. So across the period, ionization energy increases because the nuclear charge increases. There's no shielding effect. But we have exception for the trend in ionization energy across the period. And this comes when you have the full and the half full orbitals. Let's see. Okay, so if you look at the first ionization energy across the period, you see that it's increasing because there's no shielding and the nuclear charge increases. But if you now look at between oxygen and nitrogen, if you look at the electronic configuration, you see that your nitrogen is going to have px1, pyz, py1, and pz1. Can you write the electronic configuration for your nitrogen and your oxygen? Everybody, write the electronic configuration for your nitrogen and the oxygen. Write the electronic configuration for your nitrogen. For the P, we are interested in the P orbital. Try to write the P orbital in your px, py, and pz and put the electronic configuration and put the valence electrons. Okay, so if you see that, if you write out the P, you see that you are going to have, who is writing P6? So you are going to have 1s2, 2s2, 2p3. And that 2p3, you agree with me that it's going to be a half-filled stability. So that is why the first ionization energy for your nitrogen will be higher than the oxygen, because your nitrogen is actually more stable because of the half-filled stability more than your oxygen. So across the period, the first ionization energy increases due to the increase in your nuclear pool, but because of half-filled stability, you see that the first ionization energy of your nitrogen is going to be higher than your oxygen. So that is why we say there's usually an exception when we get to half-filled and completely filled orbital. So it's very, very important for you to be able to write your electronic configuration, for you to be able to answer questions on ionization energy, especially when it has to do with the trend, if there is going to be an exception in the trend. So what about ionization energy of your S and your P block? For your S and the P block, you see that your S block elements are usually metals, and the metals, they have more tendency of losing electrons, like your sodium, your potassium. They'll prefer to lose electrons than to gain. So for elements in the second and the third row of the periodic table, successive ionization energies increase steadily as electrons are removed from the valence orbitals. That is your 2s or your 2p, your 3s or your 2p, or your 3p, followed by a large increase in ionization energy when electrons are removed from field core levels. So this is actually the same, just the same as we have already explained. But I want you to note that your s orbitals, they are more of metals. So they will want to lose electrons more than your p orbitals. Your p orbitals are more of non-metals, and they will want to accept electrons to complete their octet. So that is just what I want you to know about your S and your P block element. Aside their successive ionization energies, which will increase steadily. So as you're going from your 2s, your 2p, or your 3s, or your 3p, the valence, the orbitals will have an increase in ionization energy, when electrons are removed from field core levels. So when you are writing your electronic configuration, it's very, very important for you to know if you have a field or half field core energy levels. So your forced ionization energies tend to increase across the period. I've already said this, because the valence electrons do not spin each other, allowing the effective nuclear charge to increase steadily across the period. So valence electrons are attracted more strongly by the nucleus. So atomic size decreases. So when atomic size decreases, ionization energies increases. Once the size is small, then ionization energy will increase. Okay. So the first ionization energies of the element in the first 6 rows of the periodic table illustrate 3 trends. 1, the ionization energies increase from left to right when it's across the period or across the row. The first ionization energies decrease down the group. And these are some of the, I don't need to go through the reasons again. And the third one, because as I said, the elements, they form positive ions more easily. That is your metal. This was what I was trying to explain. The elements form positive ions more steadily. So when elements form positive ions more stably, more easily, they have the lowest ionization energies. And these elements are hardest to ionize, and they usually lie in the upper right corner of the periodic table. And this is usually the metals, like your sodium, your potassium, your rubidium. They are usually harder to ionize. So, but ionization energies increase diagonally from left to right. So there's need for you to understand ionization energy down the group, across the period, if there's a half filled or completely filled orbital, if they are metals or they are non-metals, and also diagonally from left to right. Now, so we've talked about atomic radius, we've looked at ionization energy, and we have given the reasons why ionization energy will increase down the group, why it will reduce across the period, and why across the period, if there's a half filled or completely filled orbital, why there's going to be an exception, and also diagonally, and if the element is a metal or is a non-metal. Now, let's look at electronegativity. When we talk about electronegativity, okay, we talk about the, I just left that out because you might not really need it, but we can, when we talk about the inert gas configuration, that is also when we talk about the inert gas configuration, that is the stability. When you have your 288, when it's stable, of course you expect a very high ionization energy. So we can have minor deviations from this trend, and we say they can be extended in terms of particularly stable electronic configurations. We can also call it pseudo-inert gas configuration. That is when we have the partial stability or the complete stability. That is just like I explained your P3 or your 288. When you have your 288, that means you have your complete stability. So you can call it pseudo-inert gas configuration. So that is talking about your gas configuration. Of course, you know that when you talk about the inert gas configuration, you're talking about the complete stability. So this can be in the parent atom or the resulting ion. When we talk about the resulting, it can be in the atom. Maybe the atom already has the inert stability, or it's already stable. Or it can be due to ionization energy. Let's say you have an element. Okay, let's say your nitrogen, you have your px1, py1, and your pz1. If you lose the first electron from your pz, you know that element will no longer be stable. So that is the resulting ion. So you now have 2 plus. So 1 electron has been lost. So that is what we mean by resulting ion. When you have ionization energy, of course, once an electron is lost, of course, the electronic configuration will no longer be like the parent atom. So that is what we mean by pseudo-inert gas configuration. So we'll now look at electronegativity. Electronegativity is a measure of the ability of an atom in a molecule to attract electrons to itself. So what it means is that for an atom to attract electrons to itself, then we are looking at the electronegativity. And this concept was first proposed by Linus Pauling. He actually won a Nobel Prize for this effort of being able to carry out electronegativity of elements of some atoms. So when an atom is able to attract to itself electrons, then we are talking about the electronegativity. And when this occurs, let's say this is the electronegative atom. So when it can attract A, then what happens is that you now have what this is the atom will now become partially negative, and this atom will now be partially positive. So electronegativity is the ability of an atom to attract towards itself the electrons in a covalent bond. So when this happens, you now have a partially negative element or atom and a partially positive atom. And again, when we talk about electronegativity, metals tend to have low electronegativity because the metals, they want to give out electrons. So they usually have high tendency to release electrons. So metals have low tendency to attract electrons and have high tendency to release electrons. While non-metals have high tendency to attract electrons and low tendency to release electrons. So you will agree with me that the electronegativity for metals will be low, while electronegativity for non-metals will be high. So small atoms attract electrons more strongly than larger ones. When we talk about small atoms, we are talking about the size. When an atom is small, that means the nuclear pool is small. The size of that atom is small, and hence the electronegativity will be larger. We are going to, if you look at like your lanthanides, their size are usually small because they have a lot of electrons in them. Their electronic configurations is very, very high. Small atoms attract electrons more strongly than large ones, and hence small atoms are more electronegative. So when an atom is small, that means the nuclear pool is much, so they will attract more electrons. Also, atoms with nearly filled shells of electrons tend to have higher electronegativities. Why? Because their electronic configurations are almost nearly filled. They want to attract an electron to acquire the stable electronic configuration. So atoms with nearly filled shells of electrons tend to have higher electronegativities. Also, if two atoms have similar electronegativities, the bond between them will be predominantly covalent. So what it means is that if the electronegativity between two atoms are small, then the atom will be predominantly covalent. But if the difference in the electronegativity between two atoms are large, then that bond will be ionic, just like your sodium and your chlorine. Your sodium and your chlorine. The electronegativity between your sodium and your chlorine is very, very large. And that is why the bond between your sodium and your chlorine is ionic. And that is why your sodium chloride is an ionic compound. But if you look at your chlorine, the electron, of course, there is an electronegative element because the electronegativity between them is not much, so they will form covalent bond. But once the electronegativity difference is much, then that bond is going to be predominantly ionic. So what is the trend? I've already looked at the electronegativity. What is the trend? So down a group in the periodic table, what happens? Again, the size of the atom increases. Therefore, the valence electrons are further away from the nucleus. And once the valence electron is further away from the nucleus, of course, there won't be any ability to attract. So what result is that there's less attraction of the nucleus for the valence electron. And for this reason, electronegativity decreases as you go down the group. So down the group, electronegativity decreases because the valence electron is further away from the nucleus. As we said, electronegativity is the ability to attract. Once the valence electron is further away from the nucleus, of course, the attraction will be less, and thus electronegativity decreases as you go down the group. What about across the period? The atoms have the same energy level, so the size decreases. And once the size decreases, of course, the attraction of the valence electron will increase. So electronegativity increases across the group, or what we say, electronegativity increases from left to right across the period. And fluorine actually has the highest, or is the most electronegative elements. So if we recap, you see that we've already talked about the periodic table. We defined what the periodic table is, ways to classify the periodic table in terms of S block, P block, D block, F block, in terms of periods, rows, and in terms of if it's a main group or if it's a transition element. We also looked about the brief history of the periodic table, the chemists that developed the periodic table, the Mendeleev. It was actually his own periodic table that we're actually using today. And then we look at the periodic properties. I told you all the periodic properties, and we now dwelt on three. That is the ionic radius, the ionization energy, and the electronegativity. And we now looked at the trends across the period and down the group. And for each of them, we try to justify why there's going to be an increase or a decrease across the period or down the group. So that is our lecture for periodic table. And then so we'll just try to take questions. So I have some questions here. Before I take the questions in the chat, I said, which one of the following statements concerning elements in the periodic table is correct? So you can just put your answers in the chat. Question 1, which one of the following statements concerning elements in the periodic table is correct? Just put your answers in the chat. In the periodic table, the elements are arranged in the order of increasing. Put your answer in the chat. Which one of the following elements has the lowest first ionization energy? So which one of the following elements has the first lowest ionization energy? For this, you agree with me, you have to know your electronic configuration for you to know which one will have the first ionization energy. So you look into cognizance if there's going to be a half filled or completely filled, or if the distance from the valence electron. So across the period, atomic size decreases due to across the period. Why would the atomic size decrease? So okay, question 1, they say A. Question 2A, correct. Question 3, yes. I don't know why people are saying question 4 is D. No, across the period, atomic size decreases. Why will atomic size decrease across the period? Because there's an increase in the force of attraction. The nuclear pool is increasing. Okay, so I think yes. So I can see that most of you got it correctly. This is another question. The electron configuration of elements. I even have the answers here, okay? Okay, it's fine. So the electron configuration of elements A, B, C are A is 2s1, B is 3s1, and C is argon 4s1. Arrange the elements in increasing order of the first ionization potential. I think I've already given you that answer. So on your own, try to do that. Why does metals have low ionization energy? Non-metals have high ionization energy. Your sodium should have the lowest first ionization energy because you look at it down the group. Your sodium is further away. Across the period, of course, ionization energy, to remove it will be very, so you need more energy. But down the group, lithium is closer to the nucleus, sodium is lower. So it will be easier for you to remove the one electron in the sodium than the lithium. So why does metals have low ionization energy? Non-metals have high ionization energy. So I will send you the questions together with the slide. So you can just go through the questions and try to answer. Favor is saying, Ma. So let's look at some questions in the chat. Favor is saying, Ma, for electronegativity, attraction of nucleus for valence electron across the period, does it reduce? For electronegativity, attraction of nucleus for valence electron across the period. Of course, it is going to increase because you are going across the period and the nuclear charge is increasing. So the ability for it to attract will increase. So attraction of valence electrons across the period will increase. It's down the group that it will reduce because the valence electrons are further away. But the electronegativity is ability to attract. Once the ability to attract is there, then it will increase. Ma, please, can we say NS1 is a half-field orbital? Yes. NS1, just like your PXY, PZY, and PXY 111. Yes, it's a half-field orbital. So, Anonymous is saying, I don't understand. I don't know what you don't understand. Okay. So, Chizara, put your question on the chat because if I unmute you, the class will be noisy. And I don't want that. Put your question in the chat or in the question and answer, and I will answer you. I've answered others. Okay. Ma, please explain pseudo in explain the pseudo inert gas. Please, ma, explain the okay. Please, can you go over your I think I've done that pseudo inert gas. Ma, in the definition of ionization energy, you mentioned isolated gas. What does it mean for a gas to be isolated? What it means is that you are dealing with one element. Ionization energy is just one element you are dealing with. So it has to be an element. And because it's an element, so that element, the gas that is being given at is an isolated gas. The gas that is coming out is just from that element. It's not like you are adding energy to a compound. No, it's an element. So it's an isolated gas. Ma, please. Pseudo inert gas, does it work for all elements or only for, it's for noble? When you say pseudo inert, it has to be for noble gases. When there's stability, that is when it works, when it's stability. Okay? So I think I've tried to answer all the questions. If I've not answered your question, for the half-filled orbital, is it possible to have one electron in a shell? Yes, I just explained it. When you have your px, py, and pz, when you have one electron in those orbitals, they are as stable as when you have them completely filled with two electrons. Okay? So, okay? So, you said that if electron is not removed but promoted, what effect will it have on the element? Then you will not be able to have the ionization energy. There will be, if you only have ionization energy value, that is, ionization energy can only occur if the electrons are completely removed. If they are just promoted, then there's no ionization energy. It's like your +3 atom. For you to have it as 2+, of course, you have to remove the extra electron. If you don't remove that electron, if you just promoted it, then you cannot have that oxidation state. So for the ionization energy, if electron is not removed but promoted, what effect will it have on the element? It will not have, you won't be able to have the oxidation state, a new oxidation state for that particular element. Mark, can you recap on the ionization and electronegativity in order of increasing or decreasing across the period? I don't think I want to go through that again. I've explained that over and over again. So please, may I explain what you mean by ionization energy increase diagonally? Yeah, so why are you saying yes, ma'am? Oluwani Femi, you asked a question and you are saying yes, ma'am. So if you look at diagonally, I don't know if you have done diagonal relationship. If you have done diagonal relationship, you see that there's a diagonal relationship between lithium and magnesium. And your lithium is in group 1, and your magnesium is in group 2. If you see the ionization energy value for the first ionization energy value for your lithium and your magnesium, so that ionization energy for your lithium is 520, while for your for your magnesium is 737. And you know that there's a diagonal relationship between your lithium and your magnesium. So what it means is that your lithium is in group 1, but your magnesium is in group 2. So your magnesium is closer to the nucleus. Your lithium is in period 1. Your period 2. Sorry, your magnesium is in period 3. So you see that your magnesium is closer to the nucleus, while your lithium is in group 1. The valence shell is, if you go down the group, is larger than the magnesium. Your magnesium is in the same group with your sodium. Sodium is first, followed by magnesium, followed by aluminum. So that you see, because there's a diagonal relationship between your lithium and your magnesium, you see that your magnesium is smaller than your sodium. But your sodium is larger than your lithium. So diagonally, your lithium and your magnesium is the same. So in terms of the size, you see that your magnesium is smaller. So the ionization energy for your magnesium will be higher than your lithium. So that is what we mean by diagonally, ionization energy will increase. Okay, you have another class. So I'll see you on Friday by 9 o'clock. I'll see you on Friday by 9 o'clock. I will post the link. I'll post my slide and the recording also. I recorded it, so it will be on your platform. So I'll see you on Friday by 9 o'clock. Thank you.